G'day, welcome back to video number 3 in this course on Early Years Math Foundations, and the title of this video is Operations Basics. I'm wondering at this point how you're going. Obviously I can't communicate with you directly through the video camera, but if you'd like to drop me a line at my email address, peter@classroomprofessor.com, or leave a comment on the website, I'd just love to have some feedback. This is fairly early in our production of Math PD courses, and so it will help us a lot to hear what you think of it, and specifically whether you think I'm taking too long. The pacing is something that I'd really like some feedback on, if you feel like doing so. So anyway, on with the content. We're following the notes again, and we're going to start looking at the basic idea behind each operation. And the reason we're looking at this just briefly is to consider the sorts of models that we can use and how we connect the models with the symbols and so on. So addition, of course, is the addition, or rather the combination of two or more sets together. We'll start with just 2, and then later on we'll add more than 2. I'm using my hands like this. I tend to wave my arms around a lot, so I'm going to try not to do that so much. Subtraction is the inverse or the reverse of addition, and I'm going to talk a little bit more about what that means for teaching operations, to think of the two operations that are in a pair. Then of course we have multiplication. So these are in order of difficulty, and so therefore the sequence in which they're taught. Multiplication is the combination of multiple sets where each set is the same size. So one way of thinking about multiplication is that it's repeated addition, but specifically where the numbers are the same. So if we added 4, 5, 8 and 12, obviously that's not multiplication, but if we add 4, 4, 4, 4 and 4, then we could consider that as multiplication and use multiplication methods and models and so on. And division, of course, is the reverse operation for multiplication. Now, the inverse operations reverse the effect of the other one. So if we add quantities together, we can later on subtract the amount that we added, and we'll get back to where we started from. And similarly with multiplication and division. And of course this is easily known by students. It's not all that complicated. But it's worth considering what happens if we rearrange the sort of standard default order for an operation. So if we think of multiplication, if we have 3 plus 5 equals something, everybody can see that's addition. So we're going to add the two numbers together. We're going to put the result of adding on the right-hand side of the equal sign. What if we had a number sentence like that? Is that addition, or is it something else? It's written as addition, but the operation that's going to be most convenient for working that out will be subtraction, because we've got the 12, so we know the sum, the total of the numbers, and we know one of the numbers, we don't know the other one, and so we can help our students to understand that a parallel number sentence, if you like, an equivalent one, would be to start with the 12, take away the 3 and see what's left. But note that that's fairly complex. It's not all that straightforward for students to see that, and so that will take some unpacking. As always, I would recommend that the students use materials and put the counters out with materials and basically model it physically, and I'm going to talk more later in this video about models, so that the students can see what it all means, not jump immediately to some symbolic solution that says, if we're adding and one of the numbers is not present, take the number on the right, put that first and do a subtraction. You know, that's a purely mechanical and unthinking approach. So this sort of complexity and challenging style of question, if you like, is present in any of the operations. So that was an addition example where one of the addends was missing. But we could have a subtraction question that similarly is difficult, because if we like, the difference is here but the number being subtracted isn't. So in multiplication, of course, we could have a number sentence like so, and for division, what can we have here? Something like that. So And of course, some of those, these two in particular, are not early years examples, but I'm basically illustrating a principle, and it works for all of the operations. For students to understand operations well, they need to be able to use both operations that are in the pair, so they need to be able to reverse addition, to do subtraction. They need to recognize the equivalence of the two operations, and basically develop flexibility and fluency in handling quantities and using the various operations that are available. So we shouldn't be presenting students with standard forms for each of the operations as if there's some sort of template. Something plus something equals this, something plus something equals something else, and so they all look exactly the same. We need to be mixing them around and helping our students interpret situations using the operations. So moving on to the models that we can use for representing the operations. Of course, this is true of representing the numbers themselves as well, and we've already talked about that a little bit in the first video, looking at numbers and numerals in particular. Looking at the range of numerals that we have available, we can form a bit of a continuum, or a hierarchy, if you like, of representations for the operations and the numbers that make them up. So at the most physical level, the least abstract level, if you like, we could use actual real objects. So we can do operations study in the classroom by having real objects that we're going to use. A good example perhaps would be doing some actual cooking in the classroom, if that is something that you do with your students, because you're going to be using real ingredients and real quantities, and we're not just talking about it, we're not just drawing pictures of it and symbols, but we're actually using the physical objects themselves. Real objects can include, and they're not really objects, but it can include the children themselves. So the students learning an operation can be involved in acting out an operation as people involved in a story, if the people are the subject of the mathematical question. So if we're adding people to make a group in some way in a real world story. Okay, at the next level we can use pictures or diagrams or clip art to represent real objects. And of course children are familiar with pictures in their other learning at school, and so there's not a great leap there, but it is slightly more abstract, it's slightly less real, I suppose, and physical and immediate. At the third level we have strictly mathematical models. So these are things like counters and 10 frames and base 10 materials and models for fractions and that sort of thing. And finally we have symbols. So as I said before, we could make a continuum on which we can place various representations. And what we need to keep in mind about that is that we're aiming to get to the symbols because they are the most abstract. Now we can place the representations along a continuum. If I represent this horizontally, and at the left-hand end I'm going to use the word real to talk about the actual everyday real world use of operations, and at the other end let's consider abstract representations. So the different representations, the different ways of representing an operation can be thought of as being somewhere in that continuum. And so, as I said before, down at this end we have objects, we have pictures, we have math models, and we have symbols. And so, moving from left to right, things are becoming more and more abstract. Notice the symbols are not quite at the end. They're not as abstract as they could be in a sense. Merely, and what I mean by that is the numbers themselves are truly abstract. They're truly separated from the physical world. I talked about that in the first video, so I don't want to go over that again. But even the abstracts are not even the symbols are not as abstract as the numbers themselves. They're very close to it. So when we're helping our students to understand mathematics, and when we're providing them with materials to understand what's going on, we shouldn't jump too quickly to the symbols. I think that's perhaps a problem more for teachers of older students rather than the early years students. But it's worth mentioning it anyway, because in early years you are going to use symbols, but I would recommend that students have a lot of help understanding what's going on well before they get to that point. And if a student was having trouble with the symbols, then I would come back to the left and start using other representations that are easier to see. Basically, my view is I don't want to rush anybody into using symbols, and I'm perfectly happy for students to do math and to talk about it and even record it using pictures and words, and make up stories and explain it in through other media, if you like, using material somewhere at this end, and we'll get to the symbols later. Now, we do need them to know how to write it down. I'm not suggesting for a minute we could do math without the symbols, but let's not rush too quickly to it. I get the feeling sometimes that students are pushed into using symbols really before they're ready for them. And if they get lost at the symbols level, it's difficult for them to know what on earth is going on because of the abstract nature of symbols, because so much is hidden, as I said again in the first video, looking at number systems. The rules for the system are hidden, and the understanding of the rules is always quite complex and detailed and even somewhat abstract. So we shouldn't, I think sometimes there can be a reluctance to use too many models and too many physical materials. I don't think that's a problem. I don't think there's anything that we need to be concerned about if students are using materials. So, as I've said in the notes, the classroom models, the math models that we use, the 10 frames and counters and so on, are a sort of halfway point between real-world mathematics and symbols. And so we use the models in a far more abstract sense. They are a more abstract way of showing mathematics, but not as abstract as the symbols. And so we're going to be working in this middle range, if you like, quite a lot, especially with the early years, which is why I'm talking about it now. The students, as I've said in the notes, will benefit from having a range of models, and I think there's a range of levels of abstractness, I think, which is relevant as well. The other thing I want to say at this point is that there should be no stigma attached to using physical representations of mathematics, the numbers and the operations. And again, I think there's a tendency sometimes, perhaps on the part of other students, to believe that whatever you're doing at this end is the baby version of mathematics, and that anybody who's a good student and is doing well at school will be at this end using symbols, and that if you have to use pictures and models and base 10 materials, you're really, you're a dummy, or you're not keeping up with everybody else, you're lacking in some level of intelligence or something like that. And as I've said already, we are moving students in this direction, and we want everybody to be competent and proficient and able to use symbols in advanced ways, mainly when they're older, but that is the direction we're going in. But as I said before, I don't think we should rush towards that too early. And in my view, students should be able to feel comfortable about using the models almost as long as they want to. Now, obviously you've got to manage their behaviour, and we don't want anybody wasting time and just playing with the materials instead of doing their math learning. But if it's helping them, providing they're not using them as a counting device or something like that, but if it's genuinely helping them to understand, then why not use it? So my recommendation would be to have lots and lots of materials, and to help the students understand what's going on using the materials, as I said, as long as they need to, before we move to the symbols alone. Let's move on now and look at the topic of calculators. And given that this is about early years mathematics, there's not a lot we need to say, and we're not expecting to use calculators for a whole lot. Let me just quickly make a couple of recommendations about when calculators are appropriate. They're extremely useful for helping students to learn about numbers, and specifically to learn about patterns in numbers and learn about the limits, or rather the lack of limits, on patterns and understanding numbers and so on. So the numbers that we allow our students to use in the early years are quite limited, and obviously we go up to 10, then we go to 20, and then we extend it gradually out to 100. Students can learn about many other numbers that go well beyond those limits if they have access to a calculator. So they can explore the numbers. So specifically you can say 0 plus 2 equals. And if you press equals again after that, most calculators will repeat the last operation. So it will show 4, 6, 8, 10, 12, 14, 16, 18, and it'll just keep on going. And I've seen students with calculators just going as fast as they can, because they're just enjoying seeing the numbers get bigger and bigger and bigger and bigger, and they're learning about the numbers, and they're learning about the fact that really there's no end to them, and they go on and on and on. And so it's quite powerful, I think, for students to be able to discover those things, and really just to play with calculators and see what happens when you press the buttons, and compare the mathematics that they're doing in a written form with what a calculator can do. Almost as a toy. I sort of hesitate to say that, because I don't want trivial mathematics done with calculators, like trying to make words when you turn them upside down, but useful mathematics in a playful way, I suppose. That there are times when you could say to students, take out, I'll give you calculators, because they probably won't have them in their desk. See what you can find. Today we're going to look at addition and subtraction. Try entering some numbers, see what happens, and just in a very, very open-ended, as I said, playful way, let the students use them. Okay, back to the notes. Calculators will work out answers really, really fast, as we all know. They almost never make a mistake. The only one making a mistake is the human being pushing the buttons, and so they're, in a sense, they're almost flawless. They're really fast, and it's understandable that some educators and some lay people, non-educators, would say, for goodness sake, why are we still wasting time with blocks and counters? Just give every kid a calculator and let's move on. Now, because of what I've already said in this course, I don't agree with that proposition, and I'm talking a lot about using models and, quite a lot of difficult thinking. The reason for that is, of course, calculators don't think. And while a calculator can work out an answer, it can't solve a problem on its own. Only human beings can do that. And so we need our students, when they leave school, when they're adults, to be able to solve problems, and we want them to be able to use the best tools of the day, including calculators and computers and whatever other devices are available at the time. But none of those machines will solve a problem for anybody. The people have to do that themselves. So we're training our students at a very young age, in the early years, to start thinking mathematically and working out how to solve problems, as preparation for, obviously, later mathematics at school and then beyond into other things. So calculators will be with us for the foreseeable future, I'm certain of that. But so will mathematicians and scientists, engineers and doctors and nurses who use mathematics, because the calculator can't do it for you. So we shouldn't be afraid of using calculators, but at the same time we shouldn't assume that the calculator can take over the thinking part of math, because plainly that's not true. The other point to say, which I mentioned in the notes, is particularly when students get on to learning their number facts, a calculator is much slower to provide an answer to a basic number fact than a human being who knows the answer is. Now that may sound a little bit surprising, because, as I said, calculators are really fast, and children learning number facts tend to be a little bit on the slow side, and we'll be timing them and trying to improve their fluency and their speed, of course. But if you know 3 plus 5 is 8, and that's one of the simpler number facts, if someone says to you, quick, 3 plus 5, you just go 8. That was much faster than getting a calculator, turning it on if necessary, entering 3 plus 5 equals. Even though that's not a very long process, memorizing it in your head is quicker. And that's not a trivial example, because there are dozens of these number facts our students can conceivably learn to memorize, and a whole bunch beyond that. So we can also do what we call extended number facts, like 30 plus 50 is 80. And again, it's just as quick. And that would take even longer on a calculator. So there's lots and lots of mathematics that we can do in our heads that we want our students to do that is actually faster than a calculator, providing they learn to memorize. The other thing that process does, it reduces the cognitive demand in a problem-solving situation. I mentioned recently, I can't remember which video it was, a child in year 5 counting on her fingers so that she could add up the numbers 8 and 4 in the middle of a multiplication algorithm that was being used to work out the area of a rectangle. She was so far beyond the actual purpose of the task in the class, it just wasn't funny, and she was stuck at this level of not knowing her number facts. So sorry, I lost my point. My point here is about the cognitive demand. If you can answer the question 3 plus 5 is 8 quickly, that doesn't take much of a drain on your thinking. You're not going to get tired thinking about that. You can move on to what you need to know 3 plus 5 for, move on to other things. So we're doing our students a favour if we say, memorize your number facts, learn formulae, learn how to do these operations, you know, mentally if possible, because that frees you up to do a lot more advanced mathematics later on. And students, the last point in the notes, I'll finish with this in the video, students can be taught when it's sensible to use a calculator and when it's not. Obviously, when students are really young, when children are young, they don't make a lot of decisions of their own, and initially parents or child carers, and then at school their teachers will tell them when they should do certain things. And I remember seeing children who just run around all lunchtime with a jumper on a warm day and just get boiling hot, don't even think to take it off. They do need a lot of instruction. But when they're ready for it, when they are understanding the mathematics that they're learning in math class, in a mental and physical way as opposed to an electronic way, and they learn what a calculator is and what it does and have a bit of a play with it, it would be appropriate, in my view, when the students are old enough, and the teacher will have to decide when that is, to say to them, I want you to decide, well, perhaps not even that, but have a discussion and say, if we're doing this question here, is it sensible to use a calculator for this question? And I think students are in many ways responsible enough and motivated enough in their own learning to say, no, I don't want to use a calculator for that one because I don't want to lose my own abilities. And so maybe I'm going a little bit too far for the very early students, but this is something I'd recommend for older students. I found, and I'd finish with this anecdote, I did a research study in my master's degree with students in years 5, 6 and 7, so they're aged 10, 11, 12 years old. And the study was all about choices of computational methods. So I provided them one-on-one, just one student, gave them some multiplication questions to do, gave them a calculator, a paper and pencil, and there was me and a video camera, and I asked the students to choose whether to answer the questions mentally with a paper and pencil or with a calculator. And I was really surprised to find that over and over again the students weren't willing to use a calculator, even though it was there, even though it was really quick, because they understood at some level, I believe, the value in knowing how to do it themselves and how to do written algorithms. Now, that's a bigger topic for another day. But I was pleasantly surprised to find that students in what we call the upper primary level here in Australia were able to think for themselves and make sensible decisions, and were not going to agree with the proposition that everybody should just use a calculator because it's quicker. So, as I say, I think students should be invited to be a part of the discussion about when it's sensible and when it's not, because when they're older and when they're away from you and away from mum and dad, they're going to make that decision anyway. Okay, we've come to the end of this video, and I look forward to talking to you again in the next one.